Welcome to EDU World Space.
So the electric field can be defined by the following equation. So E is equal to the derivative of the potential over the derivative of the position, R. So now if you substitute the potential that we're given, which is V is equal to positive AX squared, Y minus BX squared, BY squared. So if you substitute that, let me just get that down on paper first. So P is equal to AX squared, Y minus BXY squared. So now if we substitute that and bring it into the potential into this equation, so let me write that in black. So dr, that's a really long line. Get rid of that. And now go back to pen. So now AX minus B XY squared. So now if you compute this, so now we need to compute it for each of the components. So if you compute it for EX and so now let's solve for the position at X. So now it's dx. So with respect to X, and now let me just bring this straight down here. Whoops. All right. Let me take this here. Let me delete that, and here, let me just make it easier so that we can do this quicker. So if you move this down here and differentiate it with respect to X, you're going to get that is equal to 2 times AXY minus, and since there's X to the power 1, it just goes to the coefficient, so it's BY squared. And now we know the constants which are just given to us in the equation in the question. So if you substitute that, like, I don't think I need to write it, but if you plug it straight into our calculator, substitute the values that we get from the question, we're going to get that EX is equal to negative 6.72 volts per meter. So now that's the potential at X. So now we need to calculate the potential at Y. So if you do the same thing, so the differentiated, but this time with respect to Y, since we're calculating the potential at Y, if you bring this here, bring this down here. So now if you differentiate it with respect to Y, we're going to get that it's equal to, since there's Y to the power 1 here, it just becomes the coefficients. So AX squared. And since there's Y to the power 2 here, we bring 2 to the other side and then subtract the power. So it's minus 2BX Y. And now if we substitute the values that we get from the question straight into this formula, we can get that it's equal to negative 7.2 volts per meter squared. Always remember the units. And finally, the potential at Z. I actually don't think I need to write it out. We can just look at the above equation and remember we're differentiating with respect to Z. But just by looking at this, we can notice that there is no Z variable. So then if you differentiate with respect to Z, it's just going to equal 0. So the potential at EZ is equal to 0. So now to find the net magnitude of the electric field, we can use this following formula. So let me write this in a different color. So E is equal to, so this is the net magnitude of electric field, which is equal to EX squared plus EY squared plus EC squared. So now if we substitute the values that we just computed above we're going to get that this is equal to negative 6.72 squared plus negative 7.2 squared, and since it's just 0 for the potential at EZ, we don't need to write that down. So now if we compute this in our calculator, we're going to get that the net potential, the net electric field is 9.8 over 9.8 volts per meter. So now to find the direction of the electric field, we can just use this following formula. So let me get that in green. So the theta, let me write a bit of theta there. The angle theta is equal to the tan inverse of EY over EX. This is just to find the direction, since these two are the sides of the triangle, if you could imagine it like that. So now if you just substitute the values that we got from the previous equation, so tan negative 1 is equal to negative, this is the values that we calculated up here in black. So now it's over negative 6.72. And now if you compute this, we're going to find that it's equal to 47 degrees. So now we've calculated the magnitude, the net magnitude here, and the direction here. And that's it for this question. Thank you for